All right, well, it's 11 o'clock Central, 12 Eastern, and you know the rest. Good morning, everybody. My name is Ed Creedon, and I'm a Senior Project Manager with AST Environmental. I appreciate you all being here with us today. Our webinar today is part of our 2022 series where we are focusing on specific case studies that demonstrate the effectiveness of our remedial design and implementation process. And today's webinar is going to be given by Bill Brab. Bill is a certified professional geologist and also titled a senior remediation geologist with AST. Bill's got a great success story to share with us today for a site where we identified and filled data gaps using our quantified high resolution site characterization process known as qHRSC. And once that phase of the work was completed, we designed and implemented a remedy using the RPI technology known as BOS 200+. And as the title gives away there, you'll see that the site received an NFA in less than 2 years. So before Bill gets started, I'll remind you all that questions can be posted at any time using the chat box in your webinar control panel. And we'll save some time at the end for Q&A. I think Bill's going to run about 20 minutes or so. And then we should have a few minutes at the end for Q&A. So, and if we don't get to your question, then we will certainly reach out to you individually sometime in the near future. And also, if you have to jump off, you can catch what you missed later when we post a recording of today's talk. So thanks again for joining us, and I'll step aside now and let Bill take it away.
Yeah, thank you, Ed. Can you guys see everything and hear me all right? I've got my presentation up, and I want to make sure I selected the right window for presenting to see in full presentation mode.
All good.
Excellent. So I'm going to switch over here to the presentation and get my little pointer clicker ready, so we're ready to go. All right, yeah, so welcome everybody. Appreciate everybody taking the time out of their busy day to come and hear the webinar today. This is an interesting site that we got to work on down in Tennessee that pretty much was like a similar to a rapid characterization to remediation program to move this site forward fairly quickly. So Ed was kind enough to introduce myself as well as the topic of the discussion today. So we'll jump right in here. First thing I want to do is obviously recognize the folks that were involved throughout the project from start to finish. Obviously want to thank the Tennessee Department of Environment and Conservation, Division of Underground Storage Tanks. Doug Cantrell was the primary manager in Tennessee that worked with me on this particular site. Our client, PM Environmental Inc. of Tennessee. Project manager was David Pominski, field crew out there, Matt Alexander, Bethany Kirby, several folks that were involved on the PM side of from the certified company that oversaw from the consulting side of the project. And then Eagle Synergistic, we'll get into the HRSC part. They were the direct imaging tool provider, contractor for doing the HRSC qualitative portion of the investigation out here. I want to thank Janet Castle for being a part of the team as well on this particular project. So the site that we're looking at today is your typical UST site. Everybody in the consulting world on the environmental side has encountered this before. We can see here in the image on the left-hand side, essentially a relic remnants retail petroleum facility for distributing fuel alone, with maybe probably a small convenience store, C-store type scenario inside the building here. We can see obviously the layout of the land here with this closed facility as well as some other industrial type properties adjacent to the facility. Looking here at our map on the right hand side, at the time that this came across the desk here in my office to look at for evaluation and discussion with the team, looking primarily at a legacy UST system here off to the northeast side of the site structure, which is located here in this particular polygon that we see. And following investigation, some monitoring wells installed here for the purpose of being able to look at impacts to groundwater at the facility outside of that UST basin. And then, of course, we have leading out of the UST basin here, we have the features of the piping and dispenser islands located out near the highway adjacent to the facility for access and filling of vehicles. So looking at the chronology of the steps and activities that occurred at the facility, again, this is a former retail petroleum station located in eastern Tennessee. UST closure and the initial site investigation activities occurred in early to late 2019. The previously mentioned HRSC program screening was conducted in September 2020 after the notice to proceed was issued to characterize the site and prepare for remediation. The quantitative HRSC program, or qHRSC for short, as we call it, that's handled by AST here, was conducted shortly after the qualitative screening was done. This was completed in October 2020. And then following recalibration of the site model and looking at the updated information about the facility, you have the BOS 200 injections. We'll talk about that product later on. That was conducted in May of 2021. After implementation, we can see that following that implementation program with follow-up sampling, we have a no further action issued for the facility in May of this year. So looking at the two acronyms that we talk about, HRSC versus qHRSC, and bridging that gap. Both tools are quite valuable to assessing a site, and they have their place as far as how they're utilized in order to give a better picture and help guide further actions and responsibility at the site. So what I really want to highlight here is there's tends to be some misunderstanding in the marketplace about applying these tools at times, and I think it's important to differentiate that for folks to understand. So the HRSC, the actual direct imaging qualitative measures tools, are quite valuable for being able to rapidly define vertical and lateral extent of contaminants in the subsurface, right? So it really helps to kind of dial in where there is something worth versus where there isn't, right? These tools are also quite skilled at being able to actually identify the presence of naphthalene within the subsurface. Using the hydraulic profiling tools and the while we're doing this work, we can also identify areas of low and high conductivity, and they also help to develop these qualitative models of being able to get relative abundance of materials within the subsurface. Where they are not helpful, or where we need to go a little bit further, which is where the qHRSC comes in, they're not able to actually quantify mass in the form of actual contaminant present within the subsurface, right? So this is quite important when designing a particular remediation chemistry, is we have to actually know how much material is there to be able to design around, right? And so they also cannot differentiate between speciated components within a contaminant stream. So, looking at, the actual chlorinated solvents, for instance, can't differentiate between parent and daughter products, but specifically looking at the petroleum hydrocarbons, which you're talking about today, they can't differentiate between the chemical soup that makes up that fuel that you're actually using for your vehicle and which has been released into the subsurface, right? It can't differentiate between the phases of soil mass versus groundwater, which is quite handy for doing a chemical balance basis for doing a remediation chemistry. And these are solely for the use for being able to guide a remedial design. So the RDC itself, or the qHRSC, in this case here, as I'll talk about in the next slide, actually bridges that gap and helps to get us kind of that connection between that qualitative measure and, again, that quantitative measure to be able to move forward with an effective remediation strategy. Right, so popping in here, talking about this qHRSC, quantitative high resolution site characterization. And what we're doing here is taking actual soil and groundwater laboratory analytical data and looking at both the speciated and total mass fraction of the contaminant in the subsurface. It allows us to identify zones of residual mass that were previously missed, these data gaps that aren't present within the that weren't present within the previous conceptual site model. A lot of sampling protocols and programs require stopping, for instance, soil sampling at the first instance of groundwater. However, what we find is that there is, in fact, substantial mass that does, in fact, permeate and persist well below the water table that can provide a long-term source for groundwater contamination at a facility. As part of this as well, we're also doing detailed lithological logging, right? So we're actually taking soil cores and characterizing the soil on a per foot basis, looking at it in cross-sectional view. And then kind of the tail end of this, which is important, is this three-dimensional quantitative data can actually provide a modeling component where we can actually see this in another visualization method. So if I back up here, for instance, I didn't mention our slide on the right-hand side or our image here. We're just looking at cross-sectional view with relative concentration in soil in this case, showing the relative intensity based upon the heating code here. So you know, when we have the gradient map showing here, we have the hot lobe at depth within this particular zone with relatively lower concentrations as we move away from that point. So it helps us in this particular case with the cross-sectional view. It's one way of visualizing essentially an Excel spreadsheet or a large data set that just is a bunch of numbers, right? So this is one way of being able to visualize it. We're familiar with that. And then going back to this image here, we have a interactive three-dimensional model that we can move around, zoom in, zoom out, set different levels of gradient to be able to look at threshold levels for instance, like a site cleanup standard, where is our kind of point of no return, so to speak, for contamination versus not. And then these tools all help us set up expectations to satisfy client relation, right? So it's one of these things that we can share that assist with that. It also helps us develop cost-effective remedial approaches, right? So being able to visualize this appropriately helps us to be able to collaborate as a team and figure this out. So I mentioned previously this term RDC versus qHRSC, and I want to highlight that here on this slide because ITRC in a recent document, Optimizing Injection Strategies and In Situ Remediation Performance, had actually recognized RDC, or Remedial Design Characterization is what that acronym stands for, as an appropriate method for being able to assess a site and get enough data to have a more effective use and deployment of a remediation strategy at a facility, right? So in this particular case, I want to call out that we use RDC and qHRSC sometimes interchangeably. And the reason for this is that the RDC, being a component of the qHRSC, specifically refers to the field deployment and activities that we do on these sites. So if you hear me talk about RDC versus qHRSC, that's what I'm referring to, is the field effort that brings us this data to be able to come back to the table and do the reporting and analysis for the remedial design later. So looking at the metrics of the economics of this particular graph here that we have on the right, it's important to see that, you know, with our without our RDC, we start kind of with the preliminary investigation where these lines are essentially parallel and following the same path. But looking at our cost metrics here, looking at cost per time, we see that there's an initial added cost by doing the RDC as compared to without the RDC. But once we get into the actual remediation phase, having this level of data actually reduces in both a time and cost savings in most cases, because we can better design our remediation strategy to target the known contaminant at the facility rather than going against some best guess estimations based upon some inaccurate information. So with a lot of sites, you know, this time, you know, cost is dollars and does have its obvious effects as far as going too much versus being right on par. But time is a perishable resource. So, you know, this getting to clean up quicker is usually much more valuable in the sense of rehabilitating a property and allowing the responsible party and stakeholders involved to be able to move forward with something else once they've been able to clear the site. So kind of walking through the progression of stages of work at the site. Again, we talked about doing this initial kind of qualitative HRSC screening that we did out here. Again, this was performed by Eagle Synergistic. They had advanced 33 borings to refusal or bedrock. Obviously, that can vary depending on what you're dealing with geologically at the site, but the intent was to hit bedrock refusal. The tools they ran out here was the Optical Imaging Profiler, the electrical conductivity probe, and looking at hydraulic profiling. And again, this screening method here was used to map out essentially the sources of known contamination or anticipated contamination versus not. So essentially trying to put a box on the area of investigation that we wanted to look at closer for the purpose of quantification and actual remedial action. And the map's busy and a little bit hard to read, maybe a little bit, but the main purpose to look at here is the findings of, this is OIP number 14, if it's hard for you all to see. This is essentially the hot spot, but we can see we have a relative cooling of percent fluorescence as we move away from that kind of central point. So as the investigation moved forward, there was focus on this area, but then also confirmation or more of a looking out further to make sure that we're clear of any contamination that may still need to be addressed. And so moving forward with a little cleaner map to be able to see some of these features a little better, that OIP number 14 was situated here around RDC1/TW1 and MW5, moving into that Remedial Design Characterization or RDC. So we're now stepping forward into the actual field component of the qHRSC program, which included coming out and installing 6 soil borings, 1, 2, 3, 4, and 5 here, located across that modeled map from the HRSC that we saw before. All of those soil borings were sampled continuously from ground surface down to bedrock refusal for both VOCs and TVPH. So we're looking at, again, what we talked about before, that speciated component, as well as that total mass fraction, to be able to look at the entire picture of contaminant mass within that specific boring. At 3 of these locations, at 1, 2, and 3, where groundwater delineation was still needing to be performed, we put in some temporary wells to be able to get an idea of what the groundwater looked like in those respective zones. Again, to further assess groundwater outside of the original 4 borings that were put in before. Those were analyzed for VOCs as well, TVPH, but also for a baseline level of anions and dissolved gases. And using that data, looking at, again, comparison of the HRSC versus the qHRSC, or the RDC in this case, PM came back after the fact, shortly thereafter, and installed MW5 to assess the potential for LNAPL mobility. So looking at that hotspot from the HRSC and the data we saw within RDC1, TW1, warranted putting a permanent monitoring well in here to further assess groundwater and NAPL mobility. So the findings from the RDC, again, we talked about this quantitative measure of being able to have actual contaminant mass that we can design around, right? So this is important for, again, remediation chemistry, actually having known concentrations to be able to balance against the demand requirements for that specific product, right? So this is quite important here, looking at benzene in soil versus benzene in groundwater. Again, looking at this particular area, this is, you saw from the previous map, MW5, RDC1 located here. So that's kind of right in front of the store building. And both of what's good to see here and confirms everything that came from this study is, you know, we do have a hot spot within that one specific zone in front of the store. But then looking at concentrations outside, our cleanup level for soil is 3.8 ppm, shown by this outer boundary here on this contour. And then our groundwater cleanup here is 885 ppb. So that's located here by this specific zone here. So we can see that we have a hot spot in the middle that requires a certain level of aggressiveness, but then we have some outer areas that require some action, but maybe not as aggressive as what we see in that central area. We'll talk about that here in the next, after we talk about the product. So now, looking at the actual deployed remediation out here, talked about using BOS 200 plus. Ed kind of mentioned that in his introduction. BOS 200, for those on the call that don't know, is a product manufactured by Remediation Products Incorporated out of Golden, Colorado. It's a material that's primarily used to treat petroleum hydrocarbons, and it consists of activated carbon, specifically powdered activated carbon. It has terminal electron acceptors within it to help support the biological process that's going to be injected in parallel with it. We also have some macro and micronutrients present, and then a consortium of facultative bacteria that take advantage of all the terminal electron accepting processes that are utilized at the facility. Making it BOS 200 plus, this is an enhancement upon this original product. So this is then used on sites with higher concentration, as well as trying to expedite the process of getting to more rapid degradation in a shorter time frame, right? So getting to that time factor that we talked about on the remediation side of the RDC graph we saw earlier. So this product BOS 200 plus, we do this by taking the traditional BOS 200 we see above, but then adding an electron donor in the form of food grade starch, plus a yeast extract and some additional bacteria. And what's not listed here as well, it's important, is to include both a highly soluble form of sulfate in the form of Epsom salt or magnesium sulfate, but then also a slow release version of that in the form of food grade gypsum. So we have the initial bang of high concentration, high soluble sulfate that's present to support that sulfate reducing process, but then also something that's going to be sustained over time as those terminal electron acceptors are depleted. So getting into the actual design of the site. So again, we use BOS 200 plus out here at this particular facility. Looking at just the raw metrics of what was put in, you can see the materials in combination to make up that BOS 200 plus. What's important to note here that comes out of these qHRSC / RDCs is the ability to speciate the site based upon the mass that's identified in the updated conceptual site model. So again, we talked about earlier, you saw it from the previous graphics, area A here located within the central portion that includes OIP 14, monitoring well 5, RDC 1. This is our hotspot area with significantly higher mass than the surrounding areas, areas B through E. Okay, so at the site, we had 107 injection points across this entire 5-area design. And what's interesting to note, or what's important to note here, is that area A, because of the high mass here, we went with a tighter grid, a 5-foot grid, and actually based on the variation of contamination with depth, we further divided that into 3 vertical intervals that had different dosing based upon the mass that was present within those specific vertical intervals identified. Areas B through E were on a traditional 6-foot grid with uniform dosing from top of the treatment interval to bottom of the treatment interval. And for those that are used to looking at cost comparison and feasibility for other technologies, one of the ones that we like to do for comparison is comparing it to dig and haul. So if you can access this mass and actually excavate it and remove it from the site, we try and normalize this treatment down to cost of treating this area per treated ton. So you can see here this normalized cost is around $51.60 per treated ton that we actually addressed with this injection event. So moving to the fieldwork component of this implementation of the BOS 200 plus, just some photos just to give another lay of the land at the site and show some of the action of the team out on the facility. We can see here the injection units with the AST crew within there. We have 1 pallet of the BOS 200 carbon here ready for batching and going into the treatment stream to be able to mix it up within the batch tank up here in the front part of the trailer. We have all the raw materials staged here off to the side, keeping it dry. Obviously, it's all dry powder. We don't want it to get rained on and start clumping up and everything. So just some site management here. And again, just kind of a picture of what the facility looks like within Knoxville, Tennessee here. Looking at the storefront here with some of the PM crew running the geoprobe to be able to advance these injection points, storefront again, and we can see monitoring well number 5 here being hydraulically monitored for water level changes during injection. And then just as part of the process flow with the multiple vertical intervals of dosing, we're running multiple points here, up to 3 if I recall at a time. You can see 3 here on the image for the purpose of being able to change batches within the process of installing multiple points. So that's being performed here. And then field crew out here being working within installing the or marking the injection grid in the former UST area, monitoring well 3 located next to the store here, as well as monitoring well number 4 located here behind the trees. So again, just an idea, some visuals for getting a depiction of the site. And so one of the wrap-up slides here, just wanting to show the monitoring performance. So, it doesn't just end with deploying the technology and walking away. There is that cradle to grave follow-up sampling to be able to monitor the effectiveness here. Hopefully everybody can see this clearly. I've got a big monitor, so it looks good to me. But what I really want to highlight here is looking at groundwater VOC reductions from baseline versus right before NFA closure. And we can see average reduction across the 5 wells at the site where we're within the treatment area of around 80%. Monitoring well 5 is a little bit lower here just because we're dealing with a lot more mass in that area, but the trend is downward and indicative of reaching the site cleanup goal very quickly. Looking at the other side of that is dissolved CO2 within these wells. So those of you who look at source zone depletion metrics, we know that end byproducts of petroleum degradation is water and CO2. Compared to baseline, after the implementation of this BOS 200 plus, we had an average increase of baseline dissolved CO2 in groundwater of about 565%. So augmenting of the system did show that we did have a higher, a more rapid rate and higher biological activity. There are some other metrics that we can look at here that help us to evaluate and determine effectiveness of these injections, but just a couple of items here to look at that are quite valuable for us to compare and evaluate for moving the site towards closure. And with that, I'm going to wrap up my portion of the talk. We can move into some Q&A here. I want to thank everybody for taking the time to sit in on this webinar. AST and RPI do webinars quite frequently, and obviously want to steer you, if you have time, to go look at our webinar archive, which is shown here at the link on my last slide here. And as always, if anybody wants to reach out to me directly, I am available for any conversations or follow-up dialogue about any of the sites I talk about or that I'm working on. So feel free to email me at the address here, or you can call me at the office at your leisure. And with that, I will hand the mic back off to Ed, because he, I believe, has.
Yes, thanks, Bill. Great job as always. We do have some questions here, so we'll get right to those. Let's see, first, was MW5 also monitored to see if the BOS solution entered the well, and if so, did that occur?
We do look for the presence of particulate within the well during injection. I don't have the field notes in front of me, but in the event that there is, so the procedure for injecting around monitoring wells is to, if there is intersection and carbon that does in fact get into the well is rehabilitated at the time of sampling and redevelopment. If it's determined by the responsible party and the regulatory body that the well is not acceptable, then the decision can be made to replace it. But in this particular case here, this well is not replaced, so I'm going to assume, without going back and pulling the field notes on this, that after injection, this well was suitable for continued sampling.
Okay, very good. And now what was the total project cost, including the RDC and remediation?
That's a good question.
You mentioned normalizing it to the
Right.
dig and fall, but yeah.
Yes, I did mention that, and I don't have the numbers in front of me, but I'm going to say that with RDC and injection, you're looking at probably 200,000 based upon the amount of product and the amount of time in the field. If whoever's asked that question would like that specific number, I would be happy to look that up and provide the exact number for both RDC and injection as well.
Yeah, we can send that off to them. Okay, got a couple others here. Do you have a comparison of the initial concentrations versus the end concentrations?
As far as a visual here for this particular graph, I don't have one prepared, but relative concentrations we saw from the RDC figure, for instance, I know monitoring well 5's initial concentration was 20 ppm. If we're looking at just dissolved groundwater concentration, let me see here, we can back up to that slide so that you can actually see the initial concentrations here. Right, so looking at groundwater concentration within this particular zone here was 20.1 ppm, and soil as high as 29.9, so call it 30 ppm in soil, and this is well below the water table. The post concentrations, I mean, we could do some rough math. I know all of the wells outside of the source area were well below the cleanup standard. If I recall, monitoring well 5 was pretty close to the cleanup standard, if I recall, when the site closed, but I can't remember what that concentration was. If you wanted to look at well, I did total VOC, so you can't compare the, for instance, benzene speciated by itself, but yeah, we're looking at significant reductions across the site, but I don't have the exact numbers for comparison for the actual speciated or total mass for the end concentration at the time of closure of the site.
Yeah, certainly with that 20,000 plus micrograms per liter benzene, we're looking at the presence of LMAPL there.
Right. And LMAPL was not measured in the wells, so the MAPL was not mobile, but if we're looking at the concentrations present, we do know that it's there based upon just simple chemistry metrics, right? We know it's present, but it's not readily flowing and recoverable in the well.
Right, okay. Also, which kind of lithology and how much pressure was used while injecting?
Yeah, so the lithology out here is going to be a clay, so a pretty fine grain lithology, not super tight, but tight enough. And the pressures used out here are going to be used sufficient enough to induce soil failure. So the actual pressure metrics that are measured during injection are measured at the discharge end of the pump, and so there's essentially a normalization or a backing out of what the system pressure is based upon what it requires to get through the system. So, you know, your average pressure for soil failure is going to be probably in the 50 to 100 psi range to actually induce these propagation pressures within the formation through that clay.
And that relates to another question here, which is how are you doing the injections? Are you actually using injection wells or open borings?
That's a good question. So no, we don't use injection wells. The technology is injected as a slurry, and temporary wells or injection wells cannot be used for because the particle size would just fill up the injection well. So all of these points, if we look at some of the images here from the actual injection, so this is a GeoProbe rig advancing solid stem tools, looking at 1.5-inch rods, and these tools are advanced by direct push from top-down methods, so injecting from the shallowest interval, moving down throughout the bore and injecting under pressure and flow into the subsurface as we increase with depth. So these are dedicated points on tight grids that are abandoned immediately after completion.
Okay, so this next question, try and paraphrase a little bit. Considering the number of soil and groundwater samples that you could end up collecting on a larger site using this high density sampling program, is there a cutoff where you consider this quantitative HRSC to be considered cost effective?
That's a good question. It is a balance of how dense your grid is for the purpose of sampling versus the scale of the site and the depth of the contaminant. So that obviously has to be weighed because there is a field component of both the RDC staff from the contracting side on AST's portion. So you've got the cost of the rig plus the professional or professionals from AST that are overseeing that RDC effort, plus your oversight of your consulting staff. So there's a cost associated with that. But the benefit of the RDC program, or at least this way of doing it, is the analytical costs can be eliminated as far as the high density component. RPI, the manufacturer of the BOS technologies, does have a full environmental laboratory that provides pro bono analysis of all of these samples. And so from a remedial design standpoint, a large data set could be generated fairly quickly and with no cost for the analytical itself. And for, just to add to that, what we like to always advocate is for a subset, a small percentage of those samples for compliance purposes should be sent to a NELAC certified lab for compliance purposes. And this is valuable because the regulatory agency plus the consulting firm can take advantage of these field activities to potentially get defensible data for the purpose of regulatory decision making, whether, to determine if a particular sample is above or below a cleanup threshold, but then having that NELAC certified compliance sampling from a commercial laboratory to be able to make that determination.
Okay, so having an LNAPL site, and you mentioned that you continuously sampled through the saturated zone down to bedrock refusal. Considering it's LNAPL, what's the benefit of getting these saturated soil samples from so far below the water table?
Yeah, it's a good point. I mentioned previously that a lot of sampling programs do cease soil sampling at the groundwater interface. We find and have seen, and there's quite a bit of literature that cites that LNAPLs don't stop at the water table. If you do have sufficient hydraulic head from that release, there are instances where you can get significant penetration below the water table of LNAPL concentration and contamination. So it is important as far as a total mass balance perspective to get saturated soil data in addition to unsaturated soil data along with our groundwater data. And this is important because when we look at just a simple calculation of total mass within the system, we've illustrated this on previous presentations before, but soil mass can have a multi-level increase in contribution to the actual total mass within the system. So if we don't have that picture as part of our total model, we could be missing a very big piece of the puzzle in order to make these sites go away on a much faster rate.
Yeah, excellent point. Okay, well, looks like that's the end of the questions we have. I'd encourage anybody that comes up with questions later at any time to reach out to Bill or any of us here at AST, and we're always happy to engage with you, go through some of your site data, and really give you a no-cost evaluation of the potential for using these technologies at your contaminated site. So keep an eye out for more announcements from us for upcoming webinars. We've got more in the queue. We'll have some newsletters coming out and other ways of communicating with you to let you know when they're coming. And Bill, thanks again for a great presentation. It's very, very straightforward, easy to understand information, and really appreciate your work on that.
Yeah, thanks, Ed, and thanks everybody for taking the time to listen today.
Okay, so Everybody have a great rest of your week, and thanks again for being here with us today.